Hey everyone, Mr. J here. Welcome back to Chem Talks. Today on Chem Talks, we're going to go ahead and continue our discussion of electron configurations, and we're going to add on to what we talked about. So far, we've just kind of written the electron configurations for different atoms using s, p, d, and f orbital. Today, we're going to delve in a little bit deeper and talk about what we call electron notation. And this allows us to represent the two quantum numbers that we haven't talked about, the magnetic and the spin. We've seen where we have the principal quantum number and the orbital quantum number. We haven't seen where the other two show up. So that's what we're going to talk about today, and we'll also talk about some of the rules that govern them. So electron notations, this is simply a visual representation of the four quantum numbers. We've done half of this already when we've written the electron configuration. Remember, those four quantum numbers that we've talked about are the principal quantum number, which basically is our energy level, how far from the nucleus. We talked about our orbital quantum number, which is our shape of sublevels. Are we in S, P, D, or Fs? The magnetic quantum number we're going to get into today, or at least represented. Remember, magnetic quantum number talks about which one of the three axes is lying. Is it on the x-axis, the y-axis, or the z? And then the final quantum number was the spin, and that simply tells us, is that electron spinning clockwise or counterclockwise? And we're going to learn how to represent these last two when we do notations today. So notations, when we do these, we're going to use lines, or you can use boxes to represent each orbital. So for example, if we think about S, remember how many different possible shapes S had? It was a sphere, right? So it only had one possible orientation. So we represent that with one line. P, if you remember, that has three. It can be on X, Y, or Z axis, so we represent with three lines. What about D? How many would that have? Remember, it had five. And then if we talked about F, that's going to have 7 different positions. So D we represent with 5 lines, F with 7 lines. And then in order to represent our electrons, what we're going to do is place arrows on those lines. So we use either an up arrow or a down arrow to represent the electrons. Let me go ahead and fill this in. Okay, as I said earlier, we can use boxes rather than lines. You'll see both of them done both ways. I don't care what you do. I think lines are probably easier, a little bit quicker, so I'm happy if you use those, but be aware that you will see boxes as well. All right, so let's talk about the rules that govern how we fill in these ones. And the first one is what we call the Aufbau principle. And the Aufbau principle says that electrons enter orbitals of the lowest energy level first. So that means they're going to enter the principal quantum number 1, then 2, then 3, then 4. But they're also going to go with the S's, the P's, the D's, and the F's. Okay, so electrons fill up the bottom or the least energy levels before moving on to fill up the next higher energy levels. And that just tells us where we are putting our electrons. So, like I said, fill up the S's and the P's and the D's and the F's. The second one rule is called Pauli exclusion principle. And Pauli exclusion principle says that each orbital can only be occupied by 2 electrons. And I had a student recently tell me the way he remembers it is Pauli wants 2 crackers. Okay? Each orbital can only be occupied by 2 electrons. And the other thing about those is that those electrons must have opposite spins, meaning one spins clockwise and the other spins counterclockwise. Now for our level, that gets more detail than we need, but just understand that when there's 2 electrons on a single orbital position, they must spin in opposite direction. And finally, the third law is what we call Hund's rule. And Hund's rule that says there's no pairing of electrons in the P, D, or F suborbital. Remember, P, D, and F have more than one line. S only has one line until each of those orbital positions has at least one electron in it. So for example, if we take something like oxygen, right? Oxygen has 4 electrons in the p orbital, so each position gets 1 before we go back and fill in any more. And I just put blue, no special reason other than you can see that we're coming in. So everybody gets 1 electron before anybody doubles up. And then if we had a couple more, we'd add here or here to them as well. So 3 basic rules, yes, you will need to know those and keep them straight. Okay, so let's talk about how we make these electron notations. Okay, and here it says use circles to represent positions. We're actually going to use lines. That's what you see more commonly in it. So if we take hydrogen, what's our electron configuration? Well, hydrogen's our first element, right? So it's in principal level 1, and it's shape 1, it only has 1 electron, so we know it's 1s1. So how do we represent S? Well, there's one line for it, and it has 1 electron, so we're going to place our electron in. If we move to the right to helium, right? Helium is going to be 1s2. So once again, one line, but we're going to have 2 arrows in it. Okay? Now we don't have to worry about, with just s orbitals, about making sure that everybody has 1 before anybody has 2, because S, remember, only is represented by 1 line. Now if we do something like carbon, okay, carbon is going to have S and P, so carbon's in our second row, right? So if we think of its electron configuration, it's going to be 1s2, 2s2, and 2p2. So we represent 1s2 just like we did previously with helium. 1 line, 2 arrows. Okay, fill that in first. It's filling in the lowest energy first. Then we're going to go to 2s2. We'll fill it in. That's going to look just like the 1s2. And then remember the 2p, there are 3 possible positions with the p. 1, 2, 3. And each position gets 1 electron before anybody gets 2. So we're going to put 1 in, and then we put our second 1 in. Okay? Let me have you try fluorine on your own. Go ahead and pause the video and fill it in. And once you've got it done, come back and check. But pause, no cheating, okay? I know you guys like to cheat. So pause me real quick, fill it in, come back. Did you pause me? You need to pause me. All right, so fluorine, similar to carbon, except now we have 5 electrons in our 2p. So 1s2, 2s2 will look the same. But when we get to 3p, or the 2p5, excuse me, remember everybody gets 1 position. There's 3, and then we're going to come back in 4 and 5. Okay, we call this lone electron here, this is considered to be an unpaired electron. Unpaired because there's only one of them too. And you'll sometimes see questions about how many unpaired electrons are in an element. All right, so where are these quantum numbers we've been talking about? Well, we know from writing just electron configuration that our whole number up front, that's going to represent our principal quantum number. Okay, our letters, the S, P, D, and F, those are our orbital. Okay, what orbitals are they in? And now we get 2 new ones when we do notations. The lines, okay, represent our magnetic. Which of the axes do they lie on? And then the arrows are going to represent our spin. Okay, remember I said if you have 2 electrons on a position, they're going to spin in opposite directions. I don't really care for you guys to know is it clockwise or counterclockwise. Just know that they are opposite positions. So that's pretty easy. So now we can identify where all 4 principal quantum numbers are. There's our principal, our orbital, the lines represent the magnetic, and then the spin is represented by the different electrons. Okay guys, so that kind of wraps up the end of what we're going to be talking about with electron configuration and where electrons exactly are on a atom. So if you have any questions or don't understand this, please stop in to see me before class. Otherwise, we will go over this really quick in class and do some practice. Thanks guys. Till next time, take care.